Okay, welcome everyone to the Blue Economy CRC 4th webinar series for this year. My name is Naji Abdel Samia. I'm an academic member at the Australian Maritime College, which is part of the University of Tasmania. I'm also the Deputy Program Leader for Offshore Engineering and Technology at the Blue Economy CRC. First, we start with the acknowledgement to the country. So firstly, on behalf of the Blue Economy CRC, I would like to begin by acknowledging the traditional owners of this land in which we are hosting this webinar today. I would also like to pay my respects to elders past and present, and the Aboriginal and the Torres Strait Islanders people. The next slide, please, for the Blue Economy. So to give you a background about who we are, the Blue Economy CRC was established with a 10-year life under the Australian government CRC program in July 2019. Currently, we are 44 participants from Australia and around the globe. The purpose of the Blue Economy CRC is to perform world-class collaborative industry-focused research and training that underpins the growth of the blue economy through increased offshore sustainable aquaculture and renewable energy production. Today's webinar is about offshore engineering and technology with the recent Blue Economy Symposium, which has been taking place at the 42nd OMAE conference, which is one of the larger, if not the largest, offshore and ocean and offshore and Arctic engineering, which has been recently held in Melbourne from 11th to 16th June last month. In this webinar, we'd like to thank and invite 5 speakers from those presentations have been presented last month, as I mentioned, in OMAE. The 5 presentations will cover various topics related to offshore engineering and technology within the context of the Blue Economy. So in terms of just for the housekeeping for those presentations, so we will run them over this 100 minutes or so, but then we will keep the Q&A at the end of the webinar for almost 30 minutes or so. So please use the Q&A icon that you can see on the screen and to post your questions, and then we can discuss your questions after presentation number 5. So we have, as I mentioned, 5 speakers. From first speaker, Mr. Per Holland from DMV Norway, and then the second speaker, Assistant Professor Christian Sifjunits from the University of Chile, and then the third speaker, actually we have Dr. Hugh Prekior from the Griffith University, and then Mr. Johannes Wigernick from the University of Queensland, and lastly but not least, Dr. Adi Korniawan from the University of Western Australia. The next slide, please, Leslie.
Oh, that was all. You can introduce Per now.
Yeah, so we will start with presentation number 1. So I would like to invite Mr. Per Holland to share his slides. Mr. Per Holland is a business development manager at DMV Norway offshore classification. And the presentation is about reducing risk in design and operation of exposed high volume advanced fish farms. So without any further ado, please, over to you, Per.
Thanks very much, and thanks for introduction. And last but not least, thanks for having me on again for this webinar. Really good to be back. Yes, so the content of my presentation is, as you said, a few reflections on how to improve operational safety and reduce risk in design and operation of the exposed high volume advanced fish farms that we see are put into water in a greater and greater extent these days. Mainly due to the fact that there is quite a significant supply-demand imbalance in the market when it comes to finfish and fish farmed finfish. So make sure to keep in mind that it's about the fish, but it's also a lot more when you are moving into a more advanced operation and high volume fish farming facility. So this is more or less where we come from dealing with this kind of solutions. Exposed fish farming installations, as you can see to the right, are have to move out of the very convenient sheltered water. We need new solutions, new technology in order to improve the supply of these smart proteins from the blue field, as people say. And of course, one of the solutions are to use high volume, high capacity facilities, such as the one you could see to the left, which is a very extreme example of this. A few specifics of these new facilities that we see are put into operation, mainly in Northern Europe, but we know that other areas of the planet has similar intentions. And in China, we see several of these materializing. Very often, there are quite inventive solutions that are technically advanced, utilize traditional offshore technology in a slightly different purpose to keep a high number of finfish in one place. High capacity, which again results in a higher risk, and the consequence, the business consequence and the environmental impact of a fish escape is of course much higher. We see that a lot of marine and offshore operations are involved. Operations that usually has until now belonged to more oil and gas related activity, wind turbine installation and so on. But now we see that these kind of solutions and these kind of tasks are very much moving into the aquaculture, offshore aquaculture segment. Compared to a traditional net pen, there are a lot of activity on board going on. We have people living and sleeping on board, which is a total game changer when it comes to safety, of course. Cutting edge equipment. And one of the last facts that we should embrace when we consider the total safety of these operations are that some flag states, many of them, or many authorities are not quite matured into this kind of activity. So there are no so-called flag requirements or maritime flag requirements when it comes to these kind of operations. Here's one example of installation. Two of these installations are put into operation in the northern part of Norway, fairly high capacity. Just to set the scene more firmly, let me share with you the main categories of these kind of new solutions that we see are brought on. Mainly convenient to split it into 3 categories: open, semi-closed, and closed. So the open ones are framework made of steel, and then you put net panels to enclose this to keep the fish in one place. The other one is partly semi-closed, which means that it's actually only the bottom that are open to make sure that the seawater are changed out and fresh water are circulated, and the rest is more or less a steel bucket turned upside down and put into the sea. Usually quite large, 60 meters, 80 meters in diameter. This one is the Vard Aqua Semi example. The last one is the closed solutions. This one here is the Westcon solution, where you have various modules that you can change out. This is one we're working on at the moment. And of course, the advantages of having a closed solution is that you can get pure water from deep down, and you filter the return water, hence no waste. You actually assemble and process the solids. That was a quick summary of the different solutions. You may miss one, and that is the submerged. Usually that one is over here. So the submerged could be put in line as well. So when you have to the extreme, for example, steel giants such as these, how do we reduce the operational risk and make sure that the design is safe for operation in the next 20, 30 years? Our main focus is then split into 3 main areas. It's the asset integrity of the installation itself. It's the healthy, safety and environment of the people working on board. And last but not least, it's to prevent fish escape, the fish control. And what we have seen is very efficient is actually to implement the well-known maritime safety regime and execution model, very often called classification, and a methodology that we have seen works very efficiently in oil and gas and for regular shipping. To go a little bit more into details for these 3 different categories, let me highlight a few main points here for you. Number 1, installation and the unit itself. Several of you may recognize regular items from maritime classification, such as structural integrity, stability, mooring, machinery, and electrical instrumentation installed on board. What we have here are both DNV and I believe other class societies also has prepared a rule set and our is called the floating fish farming units and installations. The magic number is 0503, which is basically we have taken all our experience from the last 60 years of offshore maritime operation and have condensed it and tuned it for fish farming into 80-90 pager rule set that has shown to be fairly successful in the industry these days. The next one, HSE, which goes towards fire safety, life-saving, emergency evacuation, and other crucial HSE items working and living on board a maritime installation. And the requirements we put to use there are, as you are maybe relieved to see, the regular maritime codes issued by IMO, International Maritime Organization, codes such as SOLAS, LSA codes, and this is also very convenient in order for the industry and the supply chain are very comfortable with this. It's a well-known methodology and approach. The last one, preventing fish escape, where we go further into the net pen and what we call extra equipment, meaning equipment on board that may cause fish escape, even though it's not directly related to maybe the aquaculture. We have an OTG, Offshore Technical Guidance 24, fish escape prevention from marine fish farms there. So in this sense, we feel that we have covered the essentials. Let me also share with you the main activities and the main milestones when you do this maritime model, starting with design approval. Somebody is looking through the drawings and checking out that the design and arrangement on board are according to rules and regulations, everything from safety to steel strength and material grades. Then, of course, we do a construction survey at the yards, shipyards or yards, wherever that is, making sure that they actually build what is on the drawings and that special processes such as welding, heat treatment, and surface treatment are taken care of. Also making sure that the certified equipment, crucial equipment being installed on board is certified, is important. And the last item is the operational follow-up, where we, with regular intervals, go on board and advise and log the condition of the installation. And then, of course, you have a feedback loop. I want to put your attention to what we call certification, CMC, because it's sometimes there's some confusion in the industry about this. Give you a few examples of this. For example, a mooring chain needs to be certified due to the fact that it supports mooring, it supports the asset integrity itself, and of course it supports the station keeping for fish control, because if the installation drifts off, then it may collide into something or go to a grounding and be damaged, and the fish will escape and you will have a disaster. Another example, convenient to bring up cranes and lifting appliances. They need to be certified due to the health and safety of people working on board, because you don't want a collapse, or you don't want to lose the load and damage people working there. And at the same time, you don't want the machine to collapse, fall into the pen, and cause a fish escape. So it serves, the certification of these crucial items going on board serves several purposes. And this is, of course, a graphic that is commonly used of this first offshore Ocean Farm 1, as it's called, the first unit to be put in operation in Norway, but it's very popular due to the fact that it illustrates the transition from the regular oil and gas tuggers and anchor handlers, as you can see here, and it's actually operating a new and exciting segment of offshore fish farming. A few examples here from what we from the units that we have in operation already, where we have the green giant, and of course the green giant is called Jostein Albert, or Hav Farm 1 and Ocean Farm 1 are sort of pulling it to the extremes when it comes to capacity, steel weight, and cost of the installation. And then you have, for example, these 4 units called aquatras. which are small scale, operated a bit more sheltered, but still utilize some advanced technology, but are a lot lighter and a lot more cost efficient when it comes to small scale. So, you know, I find it convenient maybe to share with you some of the projects that will be, that we expect to be put online in this year and next year, just to illustrate what kind of movement we have in this industrial segment. This one here, called Norlax Hydra, is actually being built as we speak in Turkey, and expected to have first fish, as we call to be ready for operation on location May, June next year. So that is quite will happen quite soon. Capacity 3,000, about 3,200 tons per year, and with the prices of Atlantic salmon, that's going to be a fairly good business for them. Smart fish farm. This one will go really far out, really exposed. Significant wave heights around 14-16 meters with a helideck, and will be operated as a regular, more or less regular offshore installation. Aquasemi, we've spoken recently about. The Ocean Sovereign is fairly is very interesting. French owners, French initiative, combined with Italians and Chile. 3-4 of these units are being planned, meant to steam, meant to sail a little bit, not stay in one place. To round it all off, I'm just going to bring up a few reflections on the road ahead, what we find is crucial for future success of this advanced fish farming, and that is, of course, to get a control of the infrastructure. We have done a lot of work there, feel that we have covered quite a lot of ground already. Secondly is the digital solutions. Make sure that the complex and integrated digital solutions are trustworthy and are reliable. And then, of course, another 3 main items that we find very, very crucial for future success, that is biodiversity, impact of and sustainability of marine environment, the animal welfare. It's good for business to have happy fish. It's also good for market, and it's good for the fish itself, of course. And then in Europe, we have this ESG, environment, sustainability, governance, which is called for transparency and reporting regarding several things. Last but not least, I just want to tap into the digital aspect of things. And as we see it, it's the smart game, and the winner of the smart game will prevail in this industry. And this little riddle, you have probably solved it already. And that says that robust digital solutions results in sustainability and profit. You're not able to get sustainability alone unless you have digital solutions. You can have, without digital solutions, you can have sustainability, but then the profit goes out the window, and the other way around. So when it comes to risk, an operational risk in this segment, we find that winning the smart game and managing the digital integrity of digital solutions is crucial. I brought up a few examples for you here. We recognize several of these terms. Integrated software and software systems are one example. We see more and more often that advanced systems, control systems, are put to work on board, and then suddenly the system does something very inconvenient and very stupid on a very unfortunate moment of time. and safety is put to the test. So really what we're working with together with the industry now is to try to achieve a smarter way to save and sustainable aquaculture. Thanks very much. I actually made it on time, which is not a common result from my side.
Thank you very much. Yeah. Actually, there is only one question in the Q&A, and if you like, probably if you would like to, I mean, answer through the chat, or we keep it at the end, or.
Yeah, I'll have a look. Thanks very much.
Thank you very much, Bear, for again. Yeah, thank you. Now let's move to the second presentation by Dr. Heo Reiki from the Griffith University. Heo, if you can please share your slides.
Lovely, thanks, Naji.
Thank you very much. So Dr. Heo is the Deputy Director and Senior Research Fellow at the Institute for Ethics and Governance at the Griffith University, Brisbane. So over to you, please.
Terrific. Thank you
Thank you
kindly,
very much.
Naji, and thanks to the BECRC for inviting me to talk to you all here today. I'll be speaking about ethical risks in the offshore blue economy integrity system. So we'll be talking about things that can go wrong morally, ethically, when we take existing blue economy industries and operations and we move them into more exposed, further away, more high energy environments. So this is a paper that I've developed with my co-author, Professor Charles Samford, and it's research that's come from our BECRC funded project on ethics, values, and social license in the blue economy. Alrighty, so what's ethical risk? Ethical risk refers to the risk that morally wrong actions will be done or unethical consequences will result. So that means that ethical risk is related to, but separate from, legal risk and operational risk. So legal risk being the chances that you violate relevant laws or regulations or standards and then get the attention of regulators, for example, and operational risk being risks to the operations themselves from going on. Ethical risk is different to these. You can have an ethical risk that poses no legal risk or even that poses no operational risk. It's just wrongdoing that's happening, something unfair or risky that is not morally proper, but it doesn't reach the pitch of falling you on the wrong side of the law or doesn't inflame local community sentiment in a way that, for example, imperils your social license to operate. So what I'll be speaking of today is the way that ethical risk can play out for blue economy operations and specifically in offshore blue economy operations. To kick things off, I'll talk about blue economy values. I'll name 6. I'll then turn to looking at the way those blue economy values can map on to different relevant stakeholders that we might be interested in. And that'll give rise to a list of blue economy ethical concerns. How do we respond to ethical concerns in normal situations, in terrestrial and other industries? We use integrity systems to respond to ethical concerns. And so I'll explain a little bit about what that looks like. And then what do we left with? Well, integrity systems are never perfect. They are human-built institutions, and they will always leave some ethical risks behind. And the ethical risks are those concerns that aren't reliably governed by the integrity system. We'll look at the ethical risks that we might think of as being introduced by ordinary blue economy industries, and then we'll have a bit of a think about how offshore and exposed blue economy industries might change that ethical risk profile. It might improve things in some respects, but it might make us more vulnerable to concerns arising in other quarters. And then what we might do to respond constructively to ethical risks. And there's lots of different things that we might do, and they depend a little bit on who we are. But governments, industry, scientists, and engineers all can have a role to play in mitigating and responding to those risks. So I'll just kick things off by listing, we'll talk about the 6 Blue Economy ethical values, ethical principles that it seems plausible to think are relevant when we're doing work in the blue economy. These have come from a variety of different sources in our work in the project over the last couple of years, including interviews that we did, including ethical theory work that we did, but also sort of looking in a type of meta-analysis at what was out there in the existing scholarship on blue economy ethics and social license. So the 6 ones that we've coalesced around, number 1, and probably very few surprises here, I think. Number 1, environmental protection. Blue economy activities should protect things like sustainability, biodiversity, ecosystem function. Number 2, stakeholder participation. Community knowledge and engagement should play a role in blue economy decision-making. Number 3, fairness. Opportunities, risks, impacts, costs, and benefits should be fairly distributed across stakeholders. Harm prevention, things like human rights, animal welfare should be protected and respected. Beneficence, this is probably the only technical term from ethical theory that I'll use. This is just doing good in the world. So blue economy activities should do things like deliver good outcomes, including quality food, safety for workers, prosperity for local environments, employment for local workers, all of the things that are positive reasons why we think that the blue economy is worth us having and is worth us protecting. And finally, trustworthiness and accountability. This one doesn't come up so much as an ethical value that people are explicit about, but it does come up as soon as you ask people about what things they think should happen to improve things in the blue economy. Often the first things that will be on people's lips will be things like better mechanisms of governance and of accountability to improve trustworthiness. So blue economy activities and systems much demonstrate their integrity. So we've got those values. What now? Well, I'm not going to walk you through all of this table, but what we can do is we can get those ethical principles, and this is non-exhaustive. We can then apply it to the relevant stakeholders that we think are in play in a particular case, and that'll give rise to more specific ethical concerns that are at a more granular level. And so it'll be something that we can dig down a little bit into to find out what's really at risk and what's in play here. So on the left-hand side of the table, you can see those ethical principles, the 6 ones that I mentioned earlier. Then each of those are applied to key stakeholders to deliver ethical concerns. Let's just zone in now on harm prevention, just to walk you through one example case. So harm prevention, there's lots of different stakeholders in blue economy activities, and they can all be harmed in various different ways. So if we're looking at employees, obviously we might be concerned with things like worker safety failures, where employees are at risk of becoming injured or killed. With our stock animals, we might be focusing on things like animal suffering. With wild animals, so for example, birds or seals might be implicated by offshore renewable wind energy or by aquaculture, and we might be worried about disproportionate harms that might happen to them. And then also harm for consumers is obviously going to be a real issue that we're going to want to focus on, and these would be things like product safety failures, food poisoning or something like that resulting. And so we can run all those ethical principles through all the key stakeholders, and then we wind up with what's usually a very long list of ethical concerns. Once we have ethical concerns, what then? Well, we tend to want to fix ethical concerns, and we usually do it in a way that we can describe as being an integrity system. So this is a mutually supportive network of ethical standards, legal norms, institutions, and incentive structures that combine together to facilitate publicly stated goals and limit the temptation for opportunities for wrongdoing, including things like corruption. And I mentioned corruption specifically because integrity systems were developed by my co-author, Professor Charles Samford, as he analysed what had been done in the post-Fitzgerald reforms in my home state of Queensland, which during the 1980s, there was endemic political and police corruption. And it was the Fitzgerald reforms that were the first time that this type of system was used to try and combat the extent of corruption in my state. So what's it amount to? Well, the integrity system includes looking at multiple levers to human conduct. Why do human beings do stuff? Well, they do stuff for a whole bunch of different reasons. They're often motivated on the basis of economic incentives and what will work for them and make them money. They respond to legal rules and the threat of formal punishments. What they do is often shaped by the affordances of the organizational design in the institution where they work and operate, and also by ethical norms or whatever personal values that they bring to the table that will talk to you about the type of things that they want to pursue and the types of things that they will not do on the basis of their ethics. So you've got all of those different levers that you can maneuver to try and get human conduct to go in pro-social directions. And at the same time, you've got multiple institutions and you've got a real cornucopia of types of institutions that we can use to try and get things right. We've got regulators, certifiers, journalistic news media often plays a crucial role, democratic elections, NGO activism, education and research institutions like the university to which I belong, scientists, professions, professional bodies. All of these can impact in various ways on the different industries that we might be looking at, and they may help them or hinder them in getting good outcomes. And ultimately, it's the holistic interaction that matters. It's not necessarily simply what institutions you have and what organizations you create. It's the interaction between them that matters. And that's critical to try and respond to the unethical action by making it risky, inconvenient, costly, and difficult, and making ethical action more constructive, more visible, more salient, and easier to do. So the ideal is that we have a variety of institutions that are mutually supportive, so long as they're all doing the right thing, but become mutually checking once one of them starts to drift away from its publicly justified values. So what might ethical risks look like then in the blue economy? And obviously I'll only be touching on a few here. It's worth at the outset to emphasize that everything has ethical risks. There's no industry, there's no scheme of human behavior or practice that doesn't have ethical concerns that it struggles to deal with and that therefore constitute ethical risks. The blue economy inherently invites some pretty serious ethical risks. It's a dynamic and innovative industry. It has social and environmental impacts, and it operates on public resources. That's just a recipe. Those three factors are just a recipe for the fact that things can go wrong. But it also has this problem. It suffers from significant governance challenges. It's hidden away from media and often from community. It's far away from normal governance bodies. Sometimes there are unclear jurisdictions and laws. It's operating in a fluid environment where actions in one place have effects far away, and sometimes it's operating with unknown interactions and impacts on ecologies that we don't understand very well. So all of those things together mean that you have ethical concerns that are arising and that they can be tough to deal with from a normal integrity systems point of view. So what happens if we then move the blue economy activities, if we're imagining them to be relatively near shore and local to communities, we move them to more offshore, more exposed, more high energy waters? Well, that's going to change the activity's ethical risk profile, and it might change it in a good way. In fact, you might even say one of the main reasons we have for wanting to move things further offshore is precisely to change that ethical risk profile. So offshore waters may, for example, be better separated from critical fragile ecosystems, such as in estuaries or bays, near coasts and mangroves, for example. It may allow for more strategic site selection. So there's just more offshore space out there, and that gives us more freedom in trying to work out a site selection that's going to minimize other ethical or social or environmental concerns that might arise. It'll have less social impact. It's simply further away from our normal communities, and therefore you have less concerns with noise, concerns with smell, light pollution, visual amenity, and so on, and have less rival users. Obviously, there'll still be some, but compared to our nearshore users, we're probably going to be in a better space with the amount of people who are vying for the same type of space. That's particularly true in an environment like Australia, for example, would be less true if we were talking about the Mediterranean, for example. However, moving blue economy operations to more exposed waters will likely increase some ethical risks. And Per already gave us a good indication of what these might look like during his presentation that we just had. So, for example, we have an increased risk of just catastrophic failure of the system, of the structure, where we have a complete loss of the integrity of the system. And then we have issues of debris, we have financial cost, we have potentially, say, mass fish deaths or fish escapes. And if the latter, then we have environmental impacts that can stem from all of these. These can happen for aquaculture, but they can happen early attempts at wind and wave technology in particular. This was not an uncommon result. You've got increased safety risks for personnel operating in high energy environments. Obviously, if they're staying on the system, on the structure itself, then that creates certain types of risks. If they're not on the structure and then they need to be going out there for maintenance, for example, then you've got a bunch of distinct safety issues that are going to be arising in each case. You've got increased distance from terrestrial governance institutions, and perhaps more challenging to give on-site monitoring at all times compared to very local blue economy operations. We've just got less knowledge about operating in new environments, and this can have real ethical impacts. It can muddy social expectations about what's going to happen. It can cloud policymakers' decision makings, and it can weaken our economic risk judgments, which can make mistakes. And finally, even the ethical need for securing vital outcomes. So you think of the renewable energy generation that we're going to need through offshore wind for the Australian government to live up to its net zero 2050 commitments. Even that need, that positive reason ethically for having offshore wind can create its own risk, because over-eager government support can prevent effective and prudent oversight. So that's just to give you a little bit of a flavour of what the changed ethical risks might look like. I'll just zip through now how we might respond to them. Different agents will obviously have different available responses. Governments can create the entire integrity system, changing policy and law. Industry can directly control their own activities and practices. Scientists can respond to those knowledge deficits that I was talking about a moment ago, developing and sharing knowledge, helping us better manage risks and expectations. And finally, engineers can develop new technologies, making it more likely that the system can deliver the values that justify it while reducing unwanted impacts. They also improve ergonomics, that interface that's happening between human systems and environment. And by doing so, they can do it in a way that's going to promote ethical rather than unethical outcomes. All right, I'm squeezed for time, so I'll leave it there. That's just the summary of what we've gone through, with ethical principles applying to key stakeholder groups, yielding those ethical concerns, using the integrity system to respond to them, and then thinking about the ways that we can get through the ethical risks that might arise. Thanks, everyone. And if you'd like to know any more about this, or you have any comments, as well as the Q&A, feel free to just shoot me an email on that email there. Thank you, everyone.
Thank you very much for this interesting presentation, which is clearly interconnected with their presentation as well, in terms of the ethical requirement and also the risks. Now, we'd like to move to the third presentation. So I would like to invite Professor Christian Sympoisum. So Christian is assistant professor at the University of Chile in Chile, with a background in naval architecture and PhD in ocean engineering. So it's over to you, Christian, please.
Thank you very much for the invitation, and as always, a pleasure to be here in this webinar talking to you. And it's connected to my presentation, is very much connected to what we have seen in the two previous ones, because what we have done here with this work, which is the title is the determination of mooring load levels on a gauge designed for exposed aquaculture in Chile, it's basically develop a joint industry project helping those people in the industry to reduce the risks. So here it's basically have a pilot to test new technologies in order to reduce the risk for the time that we get actually in exposed waters. So just to give you an update, an outline of my presentation, we're going to talk about the aquaculture in Chile. This design that we work on in all the phases, from the experimental campaign, then the numerical simulations that we helped to carry out, up to the field data that we got with the pilot in the water. This is a work developed by people in Universidad Austral, Universidad Católica, and Valparaíso. They were the ones doing the numerical simulation. ECOSI, the company actually installing and putting all the infrastructure in the water. And IX Group, which was the company who developed all the engineering for the cage, as well as the field data collected. And this picture is how aquaculture industry looks like in Chile. We have this sort of beautiful places in the south where we pretty much work only with steel cages, as you see here in this picture. Aquaculture in Chile is using a lot of space in the south. Each one of these red dots here represent one of the particular spaces where aquaculture production can be carried out over the year. Usually we have almost 400 active fish farms, because you know that we cannot use all the spaces. We have to carry out one grow period and then leave the place for the environment to recover after the fish farm is put in place. As I told you, this is a typical fish farm in Chile. Here we have this sort of arrays of steel cages made of particular pieces that can actually are hinged together, so they are flexible. Most of the agriculture now occur in sheltered areas close to the coastline, and they always have a feeding barge, as the one that you see there in the picture, supported by small vessels. And the conditions that we have here in Chile is current speed, even in those close to shore areas, up to 3 knots, with significant wave height up to 4 meters. And all of this is driven by strong local winds. So those are the conditions for which we design these systems now. And the question is, how are we going to design these systems when we go to exposed areas that we have seen in the previous presentation? This is a question that now is imposed to all the engineers, all the people working in the industry, because the spaces are getting more scarce every time. We need more space for larger production. So in Chile, we have over the last 6 years 2 joint industry projects intended for offshore conditions. And to be true, it's more for exposed conditions. We're not thinking about going completely offshore to open areas like in oil and gas, but more exposed conditions where we're going to have open fetch, for example, 120 degrees or something like that. But we need to go further offshore. The project on the right is basically a larger cage, like the one that we already have. Is 80 by 80 meters. Again, steel cages, hinge connections with a traditional netting system. That means that we have 2 nets, one for the predator net and one for the biomass inside. On the left is the one that I'm going to show you today. It's a 40-meter diameter HDPE cage that is intended to go underwater when we have higher energy seas at the surface. In this case, this has a metal net. It's a copper alloy netting that allows the production using only one net. The problem with this net is it's quite steep. The stiffness is quite high, and also the mass, therefore the inertia of the netting. So it imposes a whole different set of challenges for the dynamic analysis that you have to do, and also the response that you're going to get from the cage when exposed to waves and currents. Just to give you an idea of how this works, as I told you, it's 40 meters in diameter. The ring that actually helps to lower the cage is 12 meters below the water surface, and the total depth of the cage is 19 meters, because we have a cone that is not here in the picture. And all of this system is connected to a ballast tank and a weight at the bottom, as you see in the picture at the right. So when you have higher energy seas, you can lower the whole system. It's designed to go underwater 5 meters below the surface. because the conditions for which we are designing are intended to, are projected that 5 meters below the water depth is going to be enough to get out of the area with the maximum energy that we're going to have. So in order to test and reduce the risk, as we were saying, we carry out a series of experiments first in a towing tank that we have here in Chile at the Universidad Austral. It's a small towing tank with 40 meters length, 3 meters width, and 1.8 meter water depth. And we have all the equipment to actually carry out experiments where we can measure the motion of the floater, we can measure forces as well as and the wave conditions that we want to test. And soon we're going to have an underwater PIV system in which with this equipment, we're going to be able to see all the structural flow in underwater systems. So first, what we did, it was carried out a series of experiments in the lab that are going to give us a lot of information for the validation of numerical codes. Usually, the numerical codes that we'll have today, like for example, Aquasim, that is a software that is quite common, or 3D, or other sort of software, even CFD software, they have been calibrated for the traditional nettings, the ones that are made out of plastics or other fibers, but they are not, there is a few data of calibration data for these numerical tools for these sort of nets that are quite different in its hydrodynamic behavior, high stiffness and high weight. So we carried out drag test for a small panel to get the drag coefficient of the net. Then we carried out drag tests for these models of cages that we have here that are all intended for the calibration of the numerical codes that we are using. And finally, we have some wave tests, again, for validation. So the dimensions here, the net panel that we have, it's quite small, but it gives us enough information. Then the open cage and closed cage. The open cage is so simple, it's just a cylinder of the net that we are using, so we can test in different conditions and have pure drag or pure wave load. In the closed cage, it has the dimensions that mimic the dimensions of the real cage, and also we include this weight at the bottom because we want to see the dynamic and the interference between the interaction between these two bodies, the cage and the weight at the bottom. When we carried out the experiments, we make sure to carry out experiments up to the current speed that we already have here in Chile, 3 knots. So we went up to 1.5 meters per second. As you can see here, we can see that the drag coefficient that we have is pretty typical for these sort of systems for cylinders in these Reynolds numbers. Here it's approximately 1.1, the maximum drag coefficient that we obtain. This drag coefficient then was fed into the numerical calculation that we did in the pre-feed stages of the design of the cage. For the case of the drag test with the simplified cages, what we did, we installed the system in the tank with this double hinge connection. So we're going to have pure drag test, and again, we carry out the experiments up to the maximum current speed that we can impose per carriage in the tank. And again, all of this data is now being used for the calibration of our numerical models. One important thing, and it's the novelty of this study, is that there is no information reported in the technical literature about the deformation of these sort of nets, because as I told you before, because of the stiffness, the weight, and also because of the geometry, we observe that the deformation is actually not what you would expect with a traditional net. As we increase the speed of the current, in this case the carriage in the tank, we see that the deformation of the front of the cage, in this case, tends to go to an angle that the maximum angle that we registered was 37 degrees. In a traditional netting for this velocity that is well over 2 knots, you will see the net at the surface of the water. But in this case, we have we see an effect that is pretty much like what happened with a chain when it gets locked. So here we see sort of a locking effect with the netting, and this is information valuable for the numerical modeling. In the wave test, we carried out this test under operational and extreme conditions, measured based on the measurements on the site. And here we see for the closed cage, we see a particular behavior in the extreme condition. We see this sort of increment on the loading, and we see pretty much like a second load effect. This effect was also seen on the field, and we at the beginning we didn't know how to explain this, but then looking at the results on the lab and also at the images that we captured at the lab, basically the issue here was that the cage and the weight at the bottom was working as a double pendulum system, and the pendulum, the motion of the ballast tank at the bottom actually induces loads on the mooring system. So this is one thing that we had to look at in the second stage of the design of the cage, because it's actually increasing the loads on the mooring system. In the pre-feed calculations that we did before checking all the data that we had at the lab, because here we had to put the cage in the water, we basically did this calculation to find the maximum load on the mooring system, because then in those mooring lines we're going to install the load cell to get the data from the field. So all of these conditions here were calculated based on the Norwegian code, where you basically use regular waves to get the maximum loading on the mooring lines. And when we got these mooring lines, then we designed the mooring system, and as you see here, it's pretty traditional rope, chain, and in case of Chile, it's quite common to use gravity anchors. All this information gave us the maximum load condition, the maximum tension that we're going to have on the cage, but now we want to test this information. So this is a technology that was developed here by IX Group. It's basically a load cell that is able to go underwater and transmit data continuously to the station in the feed barge, and then to a computer in any place in the world, so we can have real data of the mooring tension in the cage. In this case, I'm just showing a small portion of time series that we captured over the time that the cage was in the water. The cage now is installed in a different place, where we went with this cage for an entire cycle, so we already harvest the fish from this cage. But in this particular field data, that again, it's going to help us to improve the numerical simulation and the engineering on the mooring system, we can see that in this particular point, we had a quite interesting event, because we see that we have the maximum tidal range, and at the same time, we have the maximum wind speed here at the second graph. And this combination means that we're going to have the higher tension on the mooring system here at the bottom. This is quite interesting, because we see that the combination of the high tidal range with the local wind speed, high wind speed, means we're going to have higher waves, and these higher waves actually induce higher loads. It's quite logical, but we see that the contribution from the current is as important as the contribution of the wave. Usually, currents are the driven factor for the design of the mooring system here, but in such a flexible system of HDPE, waves are quite important, quite relevant, so we have to keep studying this behavior. And this is something interesting that we also observe. The total displacement that we have on the cage was almost 11 meters, so it means 25% of the diameter. And this means that probably we're going to have to rethink the pre-tension of the mooring system, because we are allowing the cage to move and deform quite a lot. And if we have multiple cages here allocated in an exposed area, probably we're going to have some sort of interference between them. So this is also information for the next step on the design. this is the next step that we're taking now. We are the cage put on the water. We saw a lot of falling, not on the net itself, but in all the equipment on the side. And we are thinking that maybe we could use different types of net, not just the metallic net, but also the traditional nets. And in Chile, we have this issue with the mussels. So now we carry out multiple tests with mussels in order to evaluate the increment of the drag force when we have real biofouling. So this is data that we're going to have at the end of the year. So in conclusion, this is the whole. I just want to show you the whole process that we carried out. This is the first step in the design process. We took a lot of information from the lab. We feed this into our numerical simulation. We get the information for the design of the cage. We build this, we put it in the water, and now we are in the second stage where we are taking all the information that we gathered, and we got some really cool, interesting information. For example, this double pendulum effect was something that we didn't have in mind, and now we know that we have to improve that, as well as the pre-tension of the system. And all of this data allow us to better model these systems in our numerical codes, and probably develop new codes for this sort of stiff nets, and also the effect of biofouling that is so particular to Chile, this hard biofouling. It has to be taken into account in the next years. So that was pretty much all my presentation. If you have any questions as well, you can shoot me an email, or you can scan the QR code and you're going to have all my information. So thank you very much.
Thank you very much, Christian, for your interesting presentation. I'm sure there will be lots of questions later on in those interesting insights and findings from your experiment and field work as well. Yeah. So thanks again. So just mindful of the time, we would like now to invite our speaker number 4, which is Mr. Johannes Wiggering. If you can share your slide, please. Johannes is currently a PhD candidate at the University of Queensland, and he's working in aquaculture as well, developing novel solutions for mitigating the sloshing issues. So without any delay, it's over to you, Johannes, please.
Thank you, Naji. Thank you for the introduction. I'm just wanting to check if my voice is coming through.
Yeah.
Good.
Okay.
All right, it's a privilege here to be talking at the Blue Economy CRC webinar. Since I was a little boy, I've been very passionate about fish and about fishing, and I've experienced firsthand, primarily in the North Sea, what overfishing means. So the fish that we tried to catch became smaller and smaller, and the size of the fish became smaller and smaller, and the quantity of the fish became less and less. So about 4 years ago, I got the opportunity to start a PhD with Professor C.M. Weng from the University of Queensland and Professor Tom Baldock. And really what this opportunity for me meant was that I was able to address the issue that I've been seeing with the depleting fish stocks globally, and make a positive contribution to the aquaculture industry. So that's what my talk is about on today. I've looked at sloshing in floating closed containment aquaculture tanks. So from roughly 1990 onwards, you see that the wild captured fisheries, they plateau. And with the ever increasing demand for fish, the supply is taken up by aquaculture. And part of that is provided by inland freshwater aquaculture, and part of that is provided by marine aquaculture. And one of the ways of farming fish in a marine aquaculture environment is with floating closed containment tank systems. And there's roughly 10 of these systems operational today. So it's a fairly novel industry, but with a huge potential for growing. So this is what fish farming in floating closed containment tanks can look like. But what you see here is that the fish are separated from the external environment by an impermeable wall. So you can think of it as a bucket. And we need to actively pump water into the bucket. And by doing so, or in doing so, we can filter that, we can ozonate that, we can oxygenate that, and optimize the fish living environment, the fish environment inside. In the same way as we pump out water, we can filter that again and we collect solid waste from the bottom, which makes this a sustainable way of fish farming in the sense that we do not affect local ecosystems. Deploying these systems in a marine environment where waves exist can cause significant problems with sloshing, which are your internal fluid oscillations, and you don't need a lot of tank motions to excite resonant sloshing, where internal fluid motions can become very large. So in this video, and I want to thank Hans Bjelland from Sinta for providing this video, it really nicely illustrates what sloshing can look like. And what is characteristic in this video is that the wave amplitude that excites this sloshing is relatively small, but if the wave period is just right, you can get very significant fluid oscillations inside. So in order to make this a successful fish farming industry, we need to address the sloshing problem. While sloshing is not a new problem, like you see it in a lot of industries worldwide, sloshing in aquaculture tanks imposes additional boundary conditions because we have got live fish inside. So we have to be mindful for that. So when designing a slosh mitigation solution for closed containment tanks, we want to have minimal internal structures because we want to optimize for the free swimming space for fish. We don't want a lot of horizontally submerged surfaces, as this is where solid waste can accumulate. Also, turbulence created with baffles, for instance, can create a lot of chaos in the water. There is a free surface requirement for direct sunlight, free surface feeding, and day-to-day inspections, and yet it needs to be a simple concept or a simple solution that is preferably modular, which can be removed and needs to be cost effective. So in my PhD, I developed a solution and we call it the slosh suppression block. And you see it on the right here. It's the green annular ring that is fixed to the internal, which is fixed internal into the containment. And it's got three main characteristics. So the top of the slosh suppression block is flush with the internal water level. The width of the slosh suppression block is wide enough to create an overtopping surface for fluid to overtop onto. And the depth of the slosh suppression block is high enough to prevent air trapping underneath as we slosh. So the proposed material that we can use to fabricate these slosh suppression blocks is HDPE. It's a well-established material in the fish farming industry. It's non-toxic. It's got excellent strength characteristics and as well as biofouling characteristics. So the key principle of mitigating sloshing with a slosh suppression block is that we modify the vertical flow structure at the internal face of the slosh suppression block to a horizontal flow by overtopping. And this creates two things. So this does two things. It reduces the sloshing amplitudes at the free surface, and it prevents the progressive buildup of sloshing energy in your fluid domain, so you prevent resonance. Also, as fluid re-enters the main fluid volume after it has overtopped, you see that it has got primarily a horizontal component which keeps disturbances to the main fluid volume to a minimum, which creates a calm environment for the fish below. So to test the effectiveness of the slosh suppression block that are developed, we did various scale model experiments in the university hydro lab facility, and we were primarily interested in the engineering aspects of the problem, which were the containment tank motions, the internal fluid oscillations, so our sloshing, and the disturbances to our main fluid volume. So the test configurations that were included were a reference case, which is our no slosh suppression block, and then we've got two cases with a slosh suppression block with the overtopping with different contraction ratios, W over R1 equal 0.25 and 0.5. And for each case of the slosh suppression block with overtopping, we had an additional case without overtopping. So we extended the internal phase of the slosh suppression block beyond the free surface and made sure it was high enough such that fluid did not overtop. And this gave us a means to assess what the effect of overtopping is. And here you see a visual comparison between overtopping and no overtopping. And pay attention to the right video image, you can really see that the water stands up along the faces of the slosher pressure block without overtopping. And on the left, you see that the fluid surface has a significantly calmer appearance. So in terms of time series, I took a couple of examples here on the slide where we compare the overtopping with a no overtopping case, and these are typical time series that result. And there's two key takeaway messages here, is that if we allow for overtopping with the slosher pressure block, we reduce sloshing amplitudes. And the second one is that we prevent the progressive buildup of sloshing energy. So we do not excite this resonance sloshing, which leads to significant large sloshing amplitudes. So we tested this for a range of wave periods and values of lambda over d, where lambda is equivalent to your wave period. And each test configuration is indicated with a color code. We tested for different wave steepnesses in regular waves. And what you see is that by adopting a slosher pressure block into your fluid domain, you see that your natural sloshing periods, they reduce. And you might say like, hey, that's great. Now you've shifted your problem to a lower wave period. However, in an absolute sense, which you can see on the right, you see that your sloshing amplitudes, they reduce. So also, what you see is that for a greater range of wave periods, so larger values of lambda over d, you see that your sloshing amplitudes, they reduce. So by sacrificing moderately higher sloshing amplitudes at lower wave periods, in an overall wave period range, you have reduced, or we reduce the sloshing amplitudes. So to get a notion of the disturbances to the main fluid volume, we injected dye, or we did dye experiments with while running the tests. And for the comparison here, we're going to look at 4 different cases. One is the no slosher pressure block. One is a case with a baffle, the top right, and that is a conventional way of how typically sloshing is mitigated in oil tankers, for example. And the bottom cases are the 2 cases with a different contraction ratios with the slosher pressure block. So while looking at this video image that I'm about to play, you have to note that dye disperses by itself. So we inject the dye, and what's really interesting to see is that with the baffle case, the dye spreads fairly violently and includes the whole fluid domain in the energy dissipation process. And with the slosher pressure block that we developed, the disturbances to the main fluid volume, they remain relatively shallow, which is, which creates this low energy environment for the fish below. So in conclusion, the slosher pressure block dam sloshing via overtopping will prevent the progressive buildup of resonant sloshing. Hereby we preserve a calm environment for the fish below, and it is a practical, simple, and cost-effective solution. And this is like the slosher pressure block can help accelerate the development of floating close containment aquaculture industry in the marine environment. And I want to finish my presentation with a recommendation for future research, because we've very much talked about the engineering aspects of it, like the tank motion, your disturbances, and your sloshing. However, we've got live fish inside. And in doing research towards floating close containment tank systems in waves, we make the assumption that fish have a certain tolerance to tank motions and to sloshing and to these disturbances before the aquaculture is negatively impacted. So in order to make this a successful operation, we really need to also address and know what the limitations are in terms of fish well-being. So this needs to be quantified in future research, and that might be fish species dependent. With that, I want to finish my presentation and thank you for your kind attention.
Thank you very much. We will call you Dr. very soon because your thesis is under examination, yeah?
Sorry, you were a bit faint there.
Yeah, we'll call you a doctor very soon, I said.
I hope so.
Yeah, thank you.
Thanks, Naji.
Thank you for a great presentation and PhD study. Yeah. So I think, lastly but not least, it's our fifth presentation for today. So I would like to invite our fifth speaker for today, which is Dr. Adi Korniawan. Dr. Adi is a research fellow with Marine Energy Research Australia. That center is actually part of the University of Western Australia. So Adi, if you like, if you please share your slide on the screen.
Yeah, it should be there. Is it there on the screen?
No, not yet.
No?
Yeah.
Okay. Try again.
Yeah, it's coming now. Yeah.
Is it there now?
Yeah, all good. Thank you very much.
Yeah, thank you, Naji, for the introduction, and it's a pleasure to be here. And thank you for the Blue Economy CRC for facilitating this webinar. So, as Naji said, this is a paper presented at the recent OMAE conference in Melbourne. So I'm going to share with you some of the work we did on the numerical modeling of the M4 with energy device that we are planning to deploy in Albany, Western Australia. So I'd like to start by acknowledging my co-authors. So Hugh and Christoph, they are leading this project. They're from UWA, and Chris Shearer and Brett Saunders from BMT, they have been instrumental behind the design and detailed design of the device. And Professor Peter Stensby is the inventor of the M4 with energy device from the University of Manchester. All right, so a bit of introduction. So the M4 project, it's funded by the Blue Economy CRC as well as the state government of Western Australia. So the idea is to build and deploy a reduced scale wave energy converter in Albany. So that's where Albany is in Western Australia, and that's where I am at the moment. So the plan is to deploy in summer, this summer, Australian summer, so that's the end of this year. And there are two distinctives for this project. So the first is to demonstrate local capabilities. So we aim to manufacture the device locally in Albany. And the second is to share learning experience from this project. Okay, just a bit of introduction of the M4 wave energy converter. So it is originated in the University of Manchester. And there has been a substantial body of work, academic publications on this device in the public domain. And it is a hinge attenuator. So you have like two rigid bodies, the front and the back bodies, and which can rotate relative to each other, relative to this hinge. And the power is absorbed through the relative rotation. And another uniqueness of this device is that it has multiple floats. So we have looked at different configurations depending on the number of floats. And the configuration that we are going to deploy in Albany has one bow float, two middle floats, and one back float. And the size of the floats, they are increasing from the bow to the stern, so from the front to the back, the floats are increasing in size, and because of that, the device can naturally align itself with the wave direction. Okay, so we have done numerical modeling of this particular device, and the model that I'm going to discuss here, we assume linear hydrodynamics, so the response is proportional to the wave amplitude. And the model starts by taking unidirectional wave as input, but we have also extended it so that it can also take spreading into account. And the model can output the motions of the device in 7 degrees of freedom. So motions along the X, Y, and Z, as well as rotations about the same axis, as well as the rotation of the back body relative to the front. And it also outputs the power, and is also able to give the loads at the hinge. So the framework we are using is called these generalized modes, which essentially the motion of any point on the device can be expressed as a superposition of shape functions multiplied by a displacement amplitude. So to get the motions and power, 7 modes are required. But because we are also interested in getting the hinge loads, we need another 5 modes, which make 12 modes in total. And I'll just discuss this briefly. So we start with this standard form of the equation of motion. Basically, we have the mass here, the added mass, radiation damping, the power takeoff damping, the stiffness, and the body velocities, which we intend to solve, and the wave excitation force here. So with the generalized mode approach, the advantage is that all the elements of the mass matrix is given by this form here. So knowing the shape functions, we can work out each element of the mass matrix. So similarly, for the hydrostatic stiffness matrix, we can also make use of the shape function. So everything is become a matter of routine work. And to get the added mass and radiation damping as well as the excitation force, we use WAMIT, which has the option to specify the shape functions and output all these parameters corresponding to the shape functions. And so having all the terms now established, we can solve this equation for the body velocity. So we do that with all 7 modes. And then once we solve that for the 7 modes, then we can plug back into this equation to get the hinge, the loads at the hinge. And we do this for each different frequency and wave heading. So we get the linear transfer function for a response of interest, which can be motion, which can be load, or etc. And with the linear transfer function, which is given here, and as well as the information on the wave, which is contained in the wave spectrum, we can do many things. So like, for example, calculating the response spectrum for a given frequency and wave direction. And we can, using that, we can estimate or calculate the response mean period, as well as the most probable maximum response for a given duration, say half hour, 1 hour, or 3 hours, depending on the requirement. And for the device that we are going to deploy, it is a reduced scale, so it's not, we are not targeting like swell waves, but we are targeting wind waves, shorter waves in the region of 5-second period. So the overall length of the device is about 20 meters. And from the bow to the front to the center is about 13 meters. And from the mid to the stern is 8 meters. And the device is about 7 meters wide. And with the numerical model, we can do a lot of things. So we can, for example, study the effect of spreading. So we can, apply different spreading parameters, which is denoted by S here, where small s means bigger spreading. So we can study what this spreading does to the power. So as you can see here, if the spreading is bigger, then the power also reduces as we expect. And also in this example here, we see that the torque is also reduced with spreading, and not shown here, but we also we can also study the effect of spreading on roll, where larger spreading gives larger roll, and also larger shear force at the hinge in the Y direction. So for this example here, we use 0.5 meters significant wave height. We apply a Jones spectrum with a standard bigness parameter of 3.3. So this is a typical wave condition to be encountered at the site, but more on that later. We can also study the effect of video damping. So depending on the value of damping we apply on the hinge rotation, we get difference as we expect. So here in this example, on the left column here, we apply a certain value of power takeoff damping, whereas on the right column here, there is no damping. So the device is free to move without any resistance on the relative rotation. And okay, so we can see here without video damping, as we expect, the hinge rotation can get larger, and we expect here up to 30 degrees relative rotation between the front and the back bodies. And we also found larger shear forces in the X as well as the vertical direction, but no effects on roll and no effects on the shear in the Y direction. That is the transverse direction. And we can do similarly for other response of interest. Okay, so bit more on the site that we are interested in deploying this device. So there's Albany there. It's about 400 kilometers south of Perth. And this is Albany, and that's the map of the region. And that is the place where we are going to deploy this device. So the water depth at the location is about 12 meters. It is sheltered from the Southern Ocean by this headland because we are not looking for swell, which is longer waves, but we are interested in wind waves, shorter waves, because we have some fetch here, and this is just an ideal location for deployment for this scale of the device. So the wind waves in the summer, and the mean period is 5 seconds, and predominantly from the east, so 90 degrees from the north. So this is a picture to give you an idea of where we are going to deploy the device. So that is where we are going to deploy. There is a small island there, and this is a historic whaling station where we used to where the whaling operation used to be in the past. And this southern coast is just exposed to the swell, which is not ideal for this deployment. Okay, so with the model we have, we can also use actual wave data at the site to give us better confidence on our prediction. Because we are interested to find out what are the expected loads we are going to get, what is the expected power and motion and so on. So to do that, we deployed a wave buoy at this location since the end of 2020, and it's been collecting data since then. But of course, we are also interested in getting longer duration data set if possible, if there is any we can use. So thankfully, there is another sensor which is operated by the Southern Port Authority in Albany. So this is an acoustic wave and current profiler. So it is located not very far from the intended site. So it's about 8 kilometers away. But we need to make sure that we can use this data to give us confidence on the data. So we did a comparison looking at significant wave height, the mean period, peak period, wave direction, as well as the wave power level at the two locations from the two sensors, and they actually agree pretty well, except the wave direction, which is expected because of refraction. So in conclusion, this gives us confidence, so we can use these two data sets interchangeably, and we use the longer data set to construct this histogram or the joint probability diagram of the wave height and mean period. You can see here that the typical wave height at the site is about 0.5 meter, and the mean period is about 5 seconds. And this is only for the summer months because we are interested to deploy the device in the summer. So with the actual data and the actual spectra like measured at the site, we can input that into the model and we can run it. The model go through all the data set, and we can plot the most probable maximum response values for any response of interest. And we plot this with the color plot here, where you can see that the critical loads are all happening for sea states close to the limiting stiffness line. And we can use, we can choose some sea states along this stiffness line and use that as our design sea states. Or we can also use the entire data set to estimate, like probabilistically, the maximum response for the duration of deployment. So just to give a brief update on the ongoing plan for deployment. So we have done seabed mapping in the site, and we've progressed from design to detailed design. So here's a snapshot of what we have currently, and it is actually ready now for fabrication. So we have also included mooring, structural, as well as the power takeoff, which is the main component of this device. And we've also recently conducted tank testing at AMC in February, and the analysis of the data is ongoing. And we are also looking to deploy some instruments during the deployment so that we can get useful data telling us the motions, the hinge angle, as well as the loads at the mooring. So this is a video from the recent tank testing that we did. And on the right here, some comparison between the measurements that we did and the predictions from the numerical model. So the agreement is pretty good. So more on this later. We have a paper accepted for presentation at the Wave and Tidal Energy Conference later this year in September. So in summary, we have developed numerical model of the M4. We have collected wave data from the site, and we have used this wave data, the actual wave data, to inform design. So other aspects of the design, takeoff, tank testing will be presented at UTech this September. Thank you very much, and I'm happy to take any question.
Thank you very much for this interesting presentation. I think now time, probably we have 10 minutes or so for Q&A with all respected speakers with us today. Yeah, so probably if I start with Per Oland from DNV.
Yes, hello.
I think thank you again for your interesting presentation and talk about the development and recent development and innovation and novel solutions for aquaculture in general. And you highlighted the issue of the fish escape. And my question is, with the new large offshore platforms, do we still see those kind of issues, incidents in current years? We have those, I mean, fish escapes events happening in, for example, if you talk about Norway or other places, please, if you can comment on this.
Yes, that's a highly relevant reflection you have there, Nagi. We haven't had any major escapes, but we had some near escapes due to the fact that you have a very rigid steel structure and a flexible net embracing it. And then, of course, in the interface areas, structural interface areas, this calls for fatigue. This is a fatigue machine in that sense. So there has been some net fatigue problems, wear and tear on net. Luckily, this has been detected fairly early. And I think in the range of 20 to 50 fishes has escaped, as at least that has been claimed. So yes, definitely there has been some learning points in this area.
Thank you very much. I think I have also a question in line to Dr. Heo, which is in line of the Q&A question being, I think, posed in this webinar. It's actually, I mean, I appreciate the ethics requirement and risks for any type of industry, and especially for the emerging blue economy industries. But my question is, how do you think those can be implemented within the framework, for example, when it comes to the life cycle from design to decommissioning? Because clearly to me, this is a gap. This is a gap. So I think if you would be able, for example, how this can be implemented in the current framework and regulations and requirement, especially for the engineering stuff that we do.
Yeah, thanks, Naji. And I think you're absolutely right to think about engineering in this context, because when we're talking about ethics and ethical risk, we're naturally going to gravitate not towards engineering, but we're going to gravitate towards law, towards policy, towards governance, and all of those areas. And all of those areas are going to be much more alive to the ethical outcomes that they want and the ethical risks that they're trying to alleviate. So when government is creating legislation or regulators are deciding on their regulatory stance, they're going to be very focused and they're going to have these types of ethical risks front of mind. With things like scientists, it can also be true that they will go out to explore a particular type of risk. But with engineers in particular, I think it is very complex, and I don't think we've got a good answer to your question yet. Because what we would want ideally is for right back at those design stages, for the engineers to be having a good idea at that stage of what are the ethical risks that this particular structure in this particular environment might be being created, and therefore what type of design can we put forward that is going to alleviate some of those risks, that is going to make even accidents less likely to happen. Of course, accidents wind up being an ethical risk, not just because of the damage they do, but because a lot of us wouldn't do the wrong thing, but we definitely would cover up accidents that we've done. So there's lots of quite subtle ways in which engineering can actually contribute significantly to the ultimate ethical outcomes we have at the end of the day. But the challenge, and you've rightly put your finger on it, and I don't have a great answer, is how we manage to get those ethical concerns inputted at those early stages to the engineers so they can think through how they can develop solutions that are going to serve us well at the pointy end.
Thank you very much for this clarification and your answer. I think it's very helpful, and I think there is a gap, and we should, address this gap in the future, I think if I move to the third speaker, Professor Christian, it's just from engineering or out of curiosity. How did you monitor the deformation? Did you use a high-speed camera, or when you talk about the towing, the model inside the towing tank, and then the model at high speed is going to be deformed? So how did you monitor that one, please?
In this case, it was quite basic. We just put some cameras underwater and we have a grid on the tank. So we just analyzed the image. We didn't have any more complex system to actually do that. We only want the angle because underwater is quite complex to measure all of this motion. Actually, now we are trying to build an acoustic system. So we're going to have some devices sort of providing a signal underwater that is going to be captured by a hydrophone. And then we want to reproduce the formation of the cage inside the tank. But it's difficult. It's quite complicated.
Thank you for that. Yeah. If I move to our speaker number 4, Mr. Johans, I think probably you had already some chat about it during the conference, but how do you correlate the sloshing modes with your motion response amplitude operators? I mean, is there any correlation between rigid body motions of the model and with the sloshing results or the response of the wave elevation inside the tank? There was any type of correlation between the two?
So the sloshing is a typical frequency phenomena. So if you take a glass of water and you move that only a slight little bit, you can get very significant sloshing responses. So what you see is that if you get, like, you've got a bit of wave energy hitting your structure, and the energy can either go into containment tank motions, or it goes into the internal fluid. And what you'll see if you hit resonance, so when all the energy very much gets absorbed into the internal fluid, is that then your tank motions they can approach zero. So you've got a tank that sits fairly still in waves, and then the sloshing inside goes very significant. Yeah. So yeah.
I'm sure we will be in touch after this webinar. Yeah. I think for Adi, Dr. Adi, we have got here in a question in the Q&A, if you have a chance to see. It was about how, when the power is being extracted using the wave energy converter, how it's going to be transported basically to the shore.
Yeah, thank you for the question. So given the scale of this deployment, because it's a reduced scale, so it's not worth actually exporting the power to shore. So the plan is to dissipate the power on board using resistors. So that's the answer.
I believe, considering the time, we are just 2 minutes away from 5:45, and we are very grateful to our speakers today. I mean, some of them, 3 of them basically calling from outside, I mean, the time zone that we have here, so it's quite late. Either it's quite early in Norway or quite late or very late, I would say, in Chile. So we are very grateful to our speaker, and I would like to thank you very much for supporting this event and this webinar, and looking forward to seeing you in the future and collaborating with you as time progresses. As a closing remark, again, this recording will be available in the coming days. So, and also for the audience and attendees, please check out our webpage for any upcoming webinar. And I think there will be some webinar coming soon in August, on the 16th of August, on the role of green hydrogen in decarbonizing the maritime industry. So please stay in touch, and I wish you all the best. Thank you.
Thanks, Naji.
Thank you very much.